In this video, we will talk about the frequency response of a second-order circuit. First of all, let's look at the circuit diagram. So this is a circuit made from RLC. You have a voltage source, and then an inductor, a capacitor, and a resistor. So let's say the source is given by VST, inductor L, capacitor C, and resistor R. Let's choose the voltage across the resistor as output resistance, output voltage, VRT. And we know the source voltage is equal to Vs cosine omega t, for example. And then we would like to know what is VRT. Specifically, if we utilize complex exponential functions, we would like to know what is the magnitude of the output voltage versus the input voltage, as well as what is the phase difference between the output voltage versus the input voltage. Since we have already discussed complex impedance, so today we will utilize this approach. So first of all, we will draw the circuit utilizing complex impedance. So we can convert all of the inductor, capacitor, and resistor into boxes. So first of all, for this inductor, its complex impedance is J omega L. And then we have capacitance, which we have for the capacitor, its complex impedance is 1 over J omega C. And then finally, we have the resistor, its impedance is just R. The source is Vs tilde, and then output Vr tilde. So now let's analyze this circuit. As you can see, after you utilize complex impedance, this one is just like a voltage divider. You can just treat the inductor and the capacitor just as a regular resistor. So basically, the output voltage, Vr tilde, will just be equal to R divided by the total impedance, which is J omega L plus 1 over J omega C plus R times Vs tilde, which can be further simplified into J omega Rc divided by 1 minus omega square Lc plus J omega Rc. So in the following, we would like to discuss what is the magnitude ratio and what is a phase ratio. So first of all, let's look at the magnitude. So for the magnitude, we can calculate the magnitude by calculating the magnitude of the numerator and then the magnitude of the denominator, and then calculate the division. So the magnitude of the numerator is just simply omega Rc, and the magnitude of the denominator is square root 1 minus omega square Lc square plus omega square R square and C square. So this is the analytical expression of the voltage magnitude, the output voltage magnitude. In the following, we would like to utilize graph to represent this output voltage, the evolution of the output voltage as a function of frequency. Specifically, we will consider 3 specific situations. Depend on the frequency value. So first of all, we would like to consider what will happen if the frequency is much smaller than the resonance frequency. In this case, we assume that this is underdamped circuit, so there is a resonance frequency 1 over square root LC, which is omega 0. So we'd like to ask, what is the frequency what is the output voltage when omega is much smaller than this than this resonance frequency? By looking at the expression of the output voltage magnitude, we will soon realize that VR over Vs, absolute value, at very low frequency is approximately equal to 1 over omega. Let's look at the expression. If omega is much smaller than 1 over LC, so in this term, actually it's dominated by 1. Also, this one is also much smaller than 1 because we assume an underdamped case. So R here is smaller than the characteristic impedance. So for the denominator, it is dominated by this constant 1. And for the numerator, the leading term is just omega RC. So what we will have is this VR over Vs is approximately equal to omega RC. So to achieve this, we utilize the leading order in the numerator and the leading order in the denominator. And secondly, let's consider what will happen if omega is equal to the resonance frequency. If omega is equal to resonance frequency, we will notice that in the denominator, the first one becomes 0. And what is left is just omega squared R squared C squared, which is the same as the leading order term in the numerator, which is omega RC. So finally, what you get is VR over Vs magnitude is equal to 1 when omega is equal to the resonance frequency. And thirdly, let's talk about when omega is much larger than the resonance frequency. When omega is much larger than the resonance frequency, the leading order term in the denominator is this omega squared LC and then square, because it's much larger than 1. It's also much larger than this omega squared R squared C squared, according to the assumption of underdamped circuit. And then for the top, the leading order is still omega RC. So we can get VR over Vs magnitude is equal to omega RC divided by omega squared LC, which is equal to R over omega L. Okay, so now let's look at the 3 different expressions. When omega is much smaller than this resonance frequency, this is roughly proportional to omega, so it's linear increase. And when omega is much larger than this resonance frequency, we get the relationship is proportional to 1 over omega, so it decays in this form. And when omega is equal to resonance frequency, actually it reaches the highest value, which is 1. So now if we would like to plot graphically the magnitude of the output voltage, let's see how we can do it. Generally, for magnitude plot, we utilize log-log scale. So for both the x-axis and y-axis, we use log. So this is omega, remember it's on log scale, and then this is VR over Vs, which is also on log scale. As we discussed, the 3 different situation has boundary as omega 0, which is the resonance frequency 1 over square root LC. When omega is much smaller than this resonance frequency, as we showed here, the output voltage is proportional to omega. On a log-log scale, this linear behavior is still a linear line. So let's draw it. So it will be like this. And then this is proportional to omega. When omega is much larger than the resonance frequency, we saw the output voltage is proportional to 1 over omega. Again, on a log scale, this is represented by a linear line. So this is 1 over omega. And when omega is equal to 1 over square root LC, the output voltage versus input voltage magnitude is equal to 1. So we get this point. So the value of this is equal to 1. If this circuit has a very high quality factor, then you will get a narrow peak, actually, around this resonance frequency. If the circuit has a high quality factor, has a low quality factor, actually, you will get a broader peak surrounding the resonance frequency. So those two slopes are still 1 over omega and omega. The reason that the width of this peak, which is called the bandwidth, is related to the quality factor is because you can verify that when omega is equal to omega 0 plus minus alpha, that is 1 over square root LC plus minus R over 2L for our circuit, then you can verify the VR over Vs will be equal to 1 over square root 2. That is, when your frequency is chosen to be away from the resonance frequency by alpha, then this peak will drop to 1 over square root 2, which is 0.707. So on this side is alpha, on the other side is another alpha. So this line width is about 2 alpha. So that's the reason the smaller the dissipation or the higher the quality factor is, the narrower this line width is. So basically, the resonance frequency divided by 2 alpha is the quality factor according to our definition. So that's the reason why the quality factor will determine the exact line shape, of this this frequency response. Okay, so this is magnitude. In the following, we can also talk about the phase. So let's write down the phase expression, VR over Vs. Now let's focus on the expression here. So VR over Vs, if you look at the phase, we know the phase will be the phase of the numerator minus the phase of the denominator. The phase of the numerator can be easily seen is pi over 2 because it's purely imaginary. And the phase of the denominator is arctangent, this term, divided by the real part. Arctangent, imaginary part, divided by arctangent, divided by real part. So we can write this as pi over 2 minus, let's rewrite the denominator expression. So again, we can discuss the phase in 3 different situations. First one is still omega much smaller than the resonance frequency. And in this situation, we can say for the denominator, 1 minus omega square LC is just approximately equal to 1. And then because it's underdamped, you can also verify that the imaginary part is also much smaller than 1. So overall, this denominator is dominated by the real part. So the phase is 0. So finally, you will get a phase of pi over 2. Secondly, if the frequency is equal to the resonance frequency, 1 over square root LC, you can calculate VR over Vs. Then for the denominator, the real part becomes 0, and then it's completely imaginary. If it's completely imaginary, then its phase is pi over 2. So you get pi over 2 minus pi over 2. So finally you get phase of 0. And finally, if omega is much larger than the resonance frequency, you will see for the denominator, the first term, omega is much larger than 1 over square root LC, so that means this is a negative number. At the same time, again, because it's underdamped, the imaginary part is much smaller than the real part. So you get a purely real number, but it's negative. So negative real numbers phase is pi. So basically you get pi over 2 minus pi, which is equal to pi minus pi over 2. Okay, so now we can again represent this phase as a function of frequency in a graphical way. Again, we can utilize log scale for the x-axis for frequency, but for phase, usually we use a linear scale for the y-axis. As we calculated, for very low frequency, the phase is positive pi over 2. And for very high frequency, the phase is minus pi over 2. So, and the boundary is, again, the resonance frequency. And at the resonance frequency, the phase is 0. Across the resonance frequency, there will be a transition region from positive pi over 2 to negative pi over 2. One can also verify that when omega is equal to omega 0 plus minus alpha, again, when you go away, when you deviate from the resonance frequency by plus or minus alpha, this is alpha, this is alpha, then your phase will become pi over 4 and minus pi over 4. So again, how steep this slope is and how fast the phase transit from pi over 2 to negative pi over 2 is dominated by the quality factor. So basically, when omega is equal to omega 0 plus minus alpha, the phase over Vs becomes negative or positive pi over 4. Okay, so far we have discussed, for a second order circuit, we discussed the frequency response of the magnitude as well as the frequency response of the phase. So in this specific second order system, for the output voltage magnitude, we can see that the maximum value is 1. So the highest voltage that you can get is the same as the input voltage. That is in resonance. Actually, you can verify in resonance, this j omega L is equal to minus 1 over j omega 0 C. So in resonance, actually, the impedance from the inductor is cancelled by the impedance from the capacitor. So after they are cancelled out with each other, it behaves like there is only this resistor in the whole circuit. So that's the reason why the output voltage is exactly the same as the input voltage in resonance. And also, the phase is 0. However, when the frequency is far away from the resonance frequency, the circuit is either dominated by the inductor or dominated by the capacitor. For example, at very low frequency, the circuit is dominated by the impedance of the capacitor. If it's dominated by the impedance of the capacitor, then you will get pi over 2 phase change from the input to output. And also, the magnitude is heavily suppressed because, as recall, at a low frequency, the capacitor behaves like open. So most voltage get dropped across the capacitor. And at a very high frequency, this inductor dominates. Remember, at high frequency, inductor behaves like open. So most voltage distribute across inductor. So the higher the frequency, the lower the output voltage. Also, because it's dominated by the inductor, you get minus pi over 2 phase change when we talk about the output voltage.